Thank you, Chairman. And I'd like to say all committee members for giving me excellent opportunity to present our recent works. The title of my talk is Mid-Infrared Passive Spectroscopic Imaging for Healthcare Sensors, Infrastructure, and Agricultural Monitoring. This is Ichiro Ishimaru, Kago University, Japan. And this study was published at last November, 2022, in Scientific Reports. Title of this journal was Glucose Emission Spectrum through Mid-Infrared Passive Spectroscopic Imaging of the Wrist for Non-Invasive Glucose Sensing. If you are interested in the study, please download this article and read it. Scientific Reports is open access journal, so download is free. I have been introducing, trying to mid-infrared spectroscopy into daily life environment. As you know, Fourier transform infrared spectrometer, so-called FTIR, that is a mid-infrared spectroscopy, has high ability for component analysis. But apparatus is relatively large and expensive, so we believe downsizing and price reduction will realize healthcare sensors in everyday life, like non-invasive blood glucose sensor. We have developed two types trial products of a proposed Fourier transform spectroscopic imager. One is two-dimensional imaging type that is a kind of temporal phase shift interferometer. And another one is one-dimensional one-shot type that is a kind of special phase shift interferometer. This apparatus could acquire two-dimensional spectral distribution within 10 seconds, and we realize palm-sized apparatus using uncooled microbolometer array sensor that will be mounted on drone. As you know, uncooled microbolometer array sensor is used for thermography. And for one-dimensional one-shot type, we could obtain one-dimensional spectral distribution on the line within frame rate, for example, 15 milliseconds. We constructed the pear-sized apparatus, also using uncooled microbolometer array sensor that will be built in smartwatch. Please watch this movie. The inside of this apparatus is very simple. Objective lens and phase shifter and imaging lens and uncooled microbolometer array sensor. And this movie shows the one-dimensional type. Almost all is charged. The diameter of objective lens is 6 millimeters, and the optical axis is less than 15 millimeters. Very small apparatus. Okay, I'll explain about the passive spectroscopy. As you know, thermography detects radiated light emitted from body heat. Body temperature is around 36 Celsius, that is approximately equivalent to 300 Kelvin. And this photo shows the mid-infrared image of human arm. Our curiosity and question is radiated light include body components information like glucose. Thermography is dependent on Planck's law. Horizontal axis of this graph shows the wavelengths, and vertical axis shows emittance. Spectral emittance is determined by these curves. And this area, I mean the integrated value of this curve, is converted into temperature and displayed as false color image, that is thermography. But originally, this emission is derived from molecular vibration. And each molecular structure has specific resonant frequencies. So the emission spectrum, due to the intrinsic vibration of molecules, in this case lambda 1 and lambda 2, has emission peaks for each component. So we expected internal body components like glucose will be estimated from emission spectrum. Next, I'll explain about the differences between active and passive spectroscopy. In the case of active spectroscopy, we use light source. That is the general mid-infrared spectroscopy. But for passive spectroscopy, we do not use the light source. Measurement unit detect the radiated light due to object temperature. In the case of active spectroscopy, light source illuminates the target and reflected light or the transmitted light are measured by measurement unit. In this case, molecular vibrations are excited by illumination and energies are absorbed as vibrational energies. A spectral absorbance corresponding to the molecular structure is acquired. But for passive spectroscopy, we do not use the light source. Measurement unit detect the radiated light from target derived from molecular vibration. In this case, we could recognize the emission peaks at the same wavelengths of absorbance peak. In this case, lambda 1, lambda 2. So active and passive spectroscopy has negative and positive relationship. This photo shows the experimental setup for non-invasive blood glucose sensor from a distance. And this photo shows the mid-infrared image of human arm. And on the right-hand graph, black dotted line shows the spectral absorbance measured by FTIR, I mean the active spectroscopy. In this case, vertical axis shows the absorbance. And the red solid line shows the spectral emittance. So in this case, vertical axis shows the emittance. And we could confirm the emission peaks at the same wavelengths of absorbance peak at 9.25 and 9.65 micrometer. And this false color image shows the emittance map whose wavelength is 9.65 micrometer. So we could confirm the mid-infrared passive spectroscopic imaging successfully detect glucose component from wrist. Next, we compare the time series changes of blood glucose concentrations between conventional technology, I mean blood collection type. And this graph shows the measurement results taken every 10 minutes from 0 to 60 minutes, I mean 1 hour, with a conventional blood collection type. The subject drank drink containing sugar around 15 minutes. Blood glucose level gradually increase from 100 milligram per deciliter to the 140 milligram per deciliter. That is the measurement result using the blood collection type. And this false color image shows the emittance map whose wavelength was 9.65 micrometer. And these numbers at the bottom of false color image indicate the measurement value by blood collection type. After subject drank drink containing sugar, blood glucose level gradually rise from 101 milligram per deciliter to 168 milligram per deciliter. And false color image changes to yellow. Yellow indicates the higher emittance than green and blue. The emittance map changes to yellow as the blood glucose level rises. So we demonstrated the feasibility of non-invasive blood glucose monitoring from a distance. And we compare the time series data of spectral emittance of subject. Blue solid line shows the measurement time series data of invasive blood glucose sensor. And red solid line shows the average emittance of 9.25 and 9.65 micrometer. These two graphs do not overlap because the unit of the vertical axis are different. But we could distinguish that there is a strong correlation between these two time series data. And we conducted similar clinical trials on 5 subjects. These clinical trials were conducted in accordance with the protocol approved by the Kagawa University Ethics Review Committee. And we plotted all data on Park's error grid. Horizontal axis shows the conventional invasive blood glucose sensor measurement value. And vertical axis shows the blood glucose level that is calculated from the standard curve using the emission intensity. 91% of data are plotted in zone A, and other 9% of data are plotted in zone B. As for US FDA, if 99% of data are in zone B, the device can be approved as a medical device. However, the number of subjects must be increased. And next, I'll compare it with the conventional technology using freestyle library that is provided by Abbott company. Freestyle library has become to be popular as CGM, continuous glucose monitoring. In this method, 7 millimeter long needle should be inserted into the skin as a patch. And this patch is 14 days consumable sensor, and dedicated reading device or iPhone can read blood glucose levels with non-contact. But it is well known that the measurement value of Freestyle Libre has time delay compared with the blood collection type. And we examined the time trend difference is blood group sugar levels between blood collection type and interstitial fluid type. I mean, the Freestyle Libre is interstitial type. And the measurement data of Freestyle Libre, I mean the interstitial fluid time in this graph, this green solid line, increased about 10 minutes later than the blood collection type. And this figure shows the understanding of mechanism for time delay. Time delay occurs as a result of blood glucose in the capillaries seeping into the interstitial fluid. And paying attention on this time delay, we try to visualize glucose maldistribution. For example, the time trend of emission intensities at this pixel. This pixel has high correlation with blood correlation type like this. In this case, we selected this pixel as vein area. And paying attention on other pixel, in this case, this pixel has high correlation with interstitial fluid type. So we selected this pixel as interstitial fluid area. And many pixels that illustrated by red pixel are selected for vascular area, and many pixels that is illustrated by yellow color are selected for interstitial area. And we suspected that there may be a large blood vessel in this area. However, we have not yet confirmed yet. But we could confirm the glucose maldistribution can be visualized. And we measured emission intensity of various body parts: forehand, forehead, cheek, forearm, and forehand. At every body part, we could distinguish the emission peaks at 9.25 and 9.65 micrometer. So we proposed healthcare sensor casually watches over people with invisible light. This apparatus is very small, so AI speaker with built-in passive spectrometer will be placed around dining table. And this AI speaker will casually measure the blood glucose levels of several people around the dining table simultaneously. And complementary, we wear the smartwatch for outdoor use. And it is easy to integrate these healthcare data on the internet. Also, we developed broadband whose wavelength is 3 to 20 micrometer spectroscopic measure. We introduced free-form mirror as interchangeable and objective and imaging lens. These free-form mirrors were offered by Narux Corporation. So we realized diffracting optical system independent from wavelengths. And also we introduced broadband mid-infrared camera whose detected wavelength region is 3 to 20 micrometer. And we measured broadband spectroscopic characters of polystyrene standard sample from 3 micrometer to 20 micrometer. This blue dotted line is the reference data measured by FTIR, and this orange solid line is the measurement results by broadband unit. In future work of this broadband unit, lactic acid with emission peaks at 5.65 micrometer and other wavelengths serve an indicator of fatigue. And ketone bodies with emission peaks at 4.65 micrometer, among others, serve as indicator of metabolic effects of dieting. Furthermore, we will also challenge the early detection of dementia by measuring amyloid beta. In other words, our method as described as spectroscopic thermography. Spectroscopic thermography means any object can be observed by thermography whose temperature is over -4 centigrade can be spectrally imaged. So not only for the glucose sensors like smart room, smartwatch, smart toilet, and also large component analyzer, glucose, ethanol, glutamic acid, and also we want to apply our method to smart satellite and drones for agriculture, forestry, and fishery watch, like identification of microplastics, soil component analysis, forecast of red tide, and remote sensing for vegetation. And also we want to try to visualize degree of risk on the spot by visualizing the gas species and or the concrete damages or the forged sentence or the cultural assets preservation. For example, we are attempting to adapt our method for food composition monitoring. For ripeness of fruit, conventional method assesses through destructive inspection using refractive index analysis. But the proposed method can measure the sweetness through non-destructive inspection by monitoring camera. And as for degree of fermentation, conventional method involve analysis collecting samples and conducting measurement in laboratory with a time-consuming process. But the proposed method enable remote monitoring of the degree of fermentation using monitoring camera. And we've already measured fruits with passive spectroscopic imaging, Muscat grape, and apples. And in this case, we could distinguish the emission peaks of glucose. Okay, thank you very much for your kind attention.